Hello everyone, how are you doing today? I hope you are all very well in both health and spirit. In this presentation, I would like to share with you a major topic that I have worked on in the past years. Here, we have used density functional theory-based first principles calculations to gain insights into the design of poison-resistant catalysts for methane conversion. This problem is important because one of the greatest challenges and a long-standing problem in catalysis is the poisoning of catalytic materials that subsequently deactivates it. Catalyst poisoning is a multi-million-dollar problem in the industry. Companies have been spending so much money to replace the deactivated catalyst, so from an economic standpoint, if we can modify the catalytic materials to avoid its deactivation, millions of dollars can be saved. On the other hand, from a scientific standpoint, understanding the mechanism of catalyst poisoning and deactivation, and subsequently designing new poison-resistant materials can provide new physics that can be used to explain similar systems. Methane conversion is one of the cornerstone topics in catalysis. Since methane is an abundant feedstock that can be extracted inexpensively from shale gas and other sources, its utilization as a clean energy carrier and for the production of higher value-added commodity chemicals has triggered significant research interests over a number of decades. This presentation is divided into two parts. The first one is about avoiding carbon formation or coking on nickel catalysts for methane reforming. The next part is about avoiding sulfation or sulfur poisoning on palladium-based catalysts for methane oxidation. In this video presentation, I will focus on part 1. Part 2 will be presented in the next video. The results that I will present are based on a paper that we have published in a Nature Research journal called Scientific Reports. It is entitled Tuning Methane Decomposition on Stepped Nickel Surface, Role of Subsurface Atoms in Catalyst Design. One method of converting methane into high-value chemicals is through a process called reforming that produces synthesis gas or syngas for short. Methane molecules react with either water molecules, H2O, carbon dioxide, CO2, or oxygen for steam reforming, dry reforming, and partial oxidation reactions respectively. The produced syngas, which is composed of hydrogen and carbon monoxide, are then used for the synthesis of higher hydrocarbons and high-value chemicals such as methanol, ethanol, ammonia, and alcohols. The identified catalysts for these reactions are rhodium, ruthenium, nickel, iridium, palladium, and platinum. In the industry, nickel is widely used as a catalyst for methane reforming because of its low cost and high activity towards methane reforming. However, it suffers tremendously in carbon poisoning that deactivates it. A nickel surface was found to be active in the decomposition of methane into atomic carbonate atoms that serve as the nucleation site for the formation of carbon nanostructures that deactivates the catalyst. So in this study, we use DFT calculations to understand why nickel is active in the formation of carbon on the surface. Prior to this study, we performed DFT calculations for the overall reaction comprising a methane reforming reaction. The overall reaction can be divided into three parts. First, you have the decomposition of methane into CHX species. Here, X is equal to 0 to 3. The activation or dissociation of water molecules for the case of steam reforming, shown in this figure, or CO2 or O2 for dry reforming and partial oxidation reactions, respectively. And finally, you have the surface reactions of CHX species with oxygen-containing molecules that produces syngas or synthesis gas. We found that one principal pathway to carbon formation is the direct decomposition of methane. In the following slides, I focus on this particular reaction, the decomposition of methane. So how does nickel catalyze the decomposition of methane? I show here the reaction energy of methane decomposition into coadsorbed CHX plus H adatoms on flat and step nickel surfaces, which were modeled respectively by 111 and 211 facets of an FCC nickel. It can be seen from the figure that a flat nickel surface prefers the CH fragment, while a step nickel surface prefers atomic carbon fragment. As I've mentioned earlier, this atomic carbon adatom becomes the nucleation site for the formation of carbon nanostructures that deactivate the catalyst. To understand the preference of the step surface for methane decomposition into atomic CH or C species on flat and step nickel surfaces respectively, we analyze the electronic properties of these systems when an atomic carbon is adsorbed on these surfaces. Note that carbon adsorbs at the hollow site of nickel 111 surface as shown in the inset figures of the top panel, while it adsorbs at the 5-fold site of the step side of nickel 211 as shown in the inset figures of the bottom panel. In these figures, I show the density of states of these systems projected on the D band of nickel with and without atomic carbon shown by the red and black plots respectively, as well as the sp states of atomic carbon when it is adsorbed on these surfaces. The inset figures show the partial charge density plots projected at the energy bound by the ellipses. For the flat surface, we note an increase in the lower tail of nickel D band upon the adsorption of atomic carbon, which we have identified to be the bonding state linking carbon with 3 nickel atoms on the surface. The figure shows the hybridization of these nickel D states with the sp states of atomic carbon. Interestingly, for carbon adsorption on step nickel surface, the highly delocalized electrons around carbon forms bonds with 5 nickel atoms from both the surface and the subsurface layers. I show in this figure the formation of new states below the D band of a clean nickel surface where a hybridization between the new nickel D states and carbon sp states are seen. The partial charge density projected on the energy range bound by the ellipse shows a delocalized 5-coordinated carbon-nickel bonding. At a narrower energy range, around this peak in the density of states, the projected partial charge density plot shows the direct interaction of atomic carbon with the subsurface nickel atom. We compared the decomposition of methane on step nickel and step ruthenium surfaces to see if the same preference to atomic carbon can also be observed on another step surface and if the noted 5-coordinated bonding of atomic carbon on nickel can also be observed. I show in this figure the comparison of the reaction energies of methane on step nickel and ruthenium surfaces. Interestingly, while a step nickel surface prefers atomic carbon as the most stable decomposition fragment, a step ruthenium surface prefers the CH fragment, as similarly noted for a flat nickel surface that I have shown earlier. Correspondingly, experiments have noted that ruthenium is not very active in carbon formation. We also compared the electronic properties of these surfaces and found interestingly that while a step nickel surface promotes a 5-coordinated carbon-nickel bonding, such interaction of carbon that involves both the surface and subsurface layers were not observed for the case of step ruthenium surface. In the lower figure here, that shows the density of states of carbon ruthenium surface, the identified bonding states between ruthenium and carbon only involves 4 atoms on the surface of ruthenium. The peak that was earlier noted on step nickel that shows the direct interaction between atomic carbon and subsurface nickel atom is not seen for the case of step ruthenium. Correspondingly, the adsorption energy of atomic carbon is lower in magnitude on ruthenium compared to nickel. Let us see how we can use these results as insights into the modification of nickel to avoid carbon formation. Because carbon adsorbs strongly at the step sites, one literature-suggested way to address carbon formation is the use of various additives, such as alkali metal salts, sulfur, boron, and gold, as well as modifying the atomic composition of the step edge. DFT-based calculations found that additives work by blocking the step sites and hence removing the active sites for carbon formation. However, the step sites are more reactive than the close-packed sites for methane activation and most of the elementary steps for methane reforming process. This is shown by this experimental result, indicating a higher turnover frequency for methane conversion on rhodium-211 surface, which is a step site or a step surface, compared to a flat 111 surface. Thus, blocking the step site is expected to result in the reduction of the reforming rate as confirmed by this experiment conducted by Wang and co-workers. Here, a small amount of silver is added to nickel. These silver atoms reside at the step site, blocking the active sites for methane reforming, resulting in the reduction of the activity. So instead of such approach, we propose a new method to avoiding carbon formation on nickel. Since it is noted that the high stability of atomic carbon can be attributed to the 5-coordinated bonding with nickel atoms at the step site, it can be inferred that this binding can be weakened by promoting the 4-coordinated bonding similar to carbon adsorption on step ruthenium surface. Thus, as an alternative approach to blocking the step sites of nickel surface to prevent carbon formation, it is interesting to determine whether substituting the subsurface atoms with another element will yield 4-coordinated bonding, thereby weakening the adsorption of atomic carbon. Such system is shown in this figure, where a row of subsurface nickel atoms is substituted by other elements M. I show in this figure the adsorption energy of atomic carbon on the step site of nickel M surfaces with various M transition metal elements. The figure shows a general trend of decreasing magnitude of adsorption energy in the order of 3D greater than 4D greater than 5D elements, with a volcano-shaped behavior for the same row of elements. This observed trend is a complex effect of contributions arising from both ligand and strain factors. I show in this figure the average Bader charge and average nickel-nickel distance, shown in this figure. The volcano-shaped behavior of Bader charges compares well with carbon adsorption energies, most pronouncedly for the cases of 4D and 5D transition metals. It can be inferred from this figure that the electron-rich step nickel surface, which is seen markedly for the cases of metals M with near half-filled d orbital, such as d4 to d7, can facilitate the noted high delocalization of electrons upon carbon adsorption, resulting in the strong adsorption of atomic carbon. Additionally, the general trend of decreasing magnitude of adsorption energy relates with the increasing average nickel-nickel distance at the step site, suggesting a possible strain effect as the atomic radius of the element M increases. Upon carbon adsorption, the step site with longer average nickel-nickel distance promotes longer carbon-nickel bond length that is farther away from M, thereby weakening its interaction with the subsurface metal atom. To understand the degrees in the adsorption energy of atomic carbon, I show the density of states similar to the one that I've shown earlier for nickel for the case of nickel-gold system as a representative material. Interestingly, similar analysis to what we have done earlier shows that the 4-coordinated bonding is achieved for this nickel-gold case. A sharp peak enclosed by this dash ellipse shows the hybridization of carbon sp states with nickel d states at a narrow energy range. Correspondingly, the absorption energy of atomic carbon is lower in this nickel-gold system compared to pure nickel. Calculation of the reaction energies for the decomposition of methane shows that the C plus 4H state is shifted to a higher energy level in the nickel-gold system compared to pure nickel. It can be reasonably inferred that the weaker binding of carbon in this identified nickel-gold system can make carbon diffusion and CC bond formation easier. However, as this new system promotes the thermodynamic preference towards CH rather than C as methane decomposition fragments, it can be argued that the stability of atomic carbon on the surface is the crucial determining factor for the design of carbon poisoning resistant catalysts. Let us compare the cascade of elementary steps comprising methane decomposition on these two surfaces. I show in these schematic diagrams the reaction energies and activation barriers for the elementary steps from the initial adsorption of methane up to its complete decomposition to atomic carbon. It can be noted that the nickel-gold alloy promotes lower activation barrier for all elementary steps compared to pure nickel, except for the final CH bond cleavage yielding atomic carbon. We use this calculated data to run a kinetic Monte Carlo simulation to understand the steady state of the surface for different temperatures. Here, we considered different elementary steps shown by these reversible chemical equations, which includes adsorption-desorption processes, surface reactions, and diffusion of molecules. In the kinetic Monte Carlo simulation, we calculated the prefactors for the Arrhenius equation for each elementary step and also considered the lateral interactions of all first nearest neighbor combinations of these molecules. The reaction was simulated by predosing the surface with 0.10 monolayer of adsorbed methane molecules. I show here the snapshot of the initial state of a 50 by 50 simulation lattice. By the way, I have noted that some of the slides that I've shown you still contain this confidential remark. These results are not confidential anymore because these were already published in the literature. I was just not able to revise these old slides. So in this slide, I compared the coverage of surface-bound species on the two surfaces at the steady state as a function of temperature. Let us focus on pure nickel surface first. At temperatures below 150 Kelvin, the surface is still dominantly covered by CH4. Above this temperature, there is a shift into the dominance of CH3 on the surface as more CH4 molecules are activated. At temperatures higher than 350 Kelvin, it can be seen that all the initially pre-adsorbed CH4 molecules are converted into atomic carbon. For the nickel-gold system, it can be seen that the plots have shifted to a lower temperature range compared to pure nickel. This can be attributed to the lower activation barriers earlier noted for the case of nickel-gold system compared to pure nickel. However, instead of atomic carbon, it can be seen that at the high temperature regime, there is a substantial coverage of CH species on the surface in addition to atomic carbon. This shows that indeed the coverage of atomic carbon on the surface is lower on the alloy system compared on pure gold. Finally, I show in these slides some ideas for alloying that emerged from this study. This particular method of modifying nickel catalysts, as illustrated by the nickel M systems, features a new approach to catalyst design where subsurface atoms are altered to discriminately tune the adsorption of a particular adsorbate, which for this case is atomic carbon, thereby changing the reaction mechanism happening on the surface. While the aim of this study is limited at demonstrating the important role of subsurface atoms in the catalysis of methane decomposition to provide insights into the atomic scale engineering of the step side of nickel surface, it is well recognized that certain metals may segregate on the surface, creating a challenge for the experimental feasibility of subsurface metal substitution for some metal catalysts. For example, the detailed characterization of silver-nickel alloy catalyst for steam reforming found that silver atoms form surface alloys and preferentially replace nickel atoms at the step side. Moreover, EXAFS or EXAFS analysis shows that at low concentrations, gold preferentially stays on the surface of nickel-gold alloy and may aggregate with increase in concentration to form small clusters. Nevertheless, with the exception of silver, palladium, and gold, the metals considered in this study have moderate segregation, just like the cases of platinum, rhodium, and copper, or no segregation, such as for the case of manganese and nickel, and anti-segregation tendencies on nickel host metal. So I hope that this study will stimulate further research interests into similar systems, taking into account factors such as surface segregation and agglomeration, and geometric and electronic effects for industrial applications. With that note, thank you very much for your very kind attention.